Now here you see a moving coordinates frame which is established on a rigid body. This may be the end effector of the robot or any link of the robot, and this point here, the P, may actually indicate any joint. So this is a general figure, and the distance and orientation, or the position and orientation of this point, are represented by a position vector, as you see, the red, and we say that the P, the point P's position vector with respect to the base frame A, and the orientation of the axis of the moving frame with respect to the original frame. So if I know how to express these mathematically, that means I can exactly represent this point with respect to the base frame. Why is this important? We have been repeating this because we want to express the joints and the motions of the end effector always with respect to the base frame. This is also going to be important in controlling the robot. In describing the rotations of the B with respect to A, we used the rotation matrix. Now let us look at the rotation matrix closer. Rotation matrix, as you remember, is a 3 by 3 matrix. 3 rows and 3 columns. And in this case, in this rotation matrix, we are showing the B frame with respect to A frame. Look, when we look at the rotation matrix, actually this position vector is not important anymore, so that we've actually transferred the B frame to the origin of the A frame. We can think of it as that the B frame is now at the origin, because now we are just concerned about how much this B frame rotated with respect to the A frame. Now, if you look at, for instance, how much XB rotated with respect to the A frame, we need to find out for this the projections of the XB with respect to A frame. In other words, what's the projection of XB along XA, along YA, and along ZA? These projections are given by multiplying the x vector. This is the x vector. Only the x component is 1. Y and z components are 0 with this rotation matrix. This is how we represent it. So, and I may also show this matrix as the projections of x b in the A frame, projections of y b in the A frame, and projections of is ZB in the A frame. Why are we bothering about this? Because we are going to see a little bit later. This type of representations help us a lot in solving some problems. So this part of the matrix shows me the projection of XP along the projections of XP along the XA, YA, and ZA. Similarly, the next column shows the projections of YB in the A frame, and finally the third column shows me the projections of Z along the frames or axis of the B frame. Let's continue. So we have seen what sort of information is in this rotation frame. A column which is showing the projections of XB in frame A, another column which shows the projections of YB in A frame, and the third column finally shows the projections of ZB in the A frame. What is the projection? Projection is obtained by the dot product. So the projections of XB, for instance, along XA is simply found by multiplying XB dot XA. Similarly, it is projection along the y-axis, YA-axis is XB dot YA. And finally, its projection along the ZA axis is XB dot ZA. And this is, as we know, is the first column. Now look at the first row. In the first row, we see that XP dot XA, YB dot XA, and ZB dot XA are actually aligned in the first row. What do these mean? If I try to project the XA to the B frame, what would I do? I would have the dot product of XA with XP, dot product of XA with YB, and dot product of XA with ZB. In other words, XA dot XP here, XA dot YB below it, and XA dot ZB below it. Okay, and remember that dot product is commutative. That is, XA dot XP is equal to XP dot XA. And if I take the transpose of it, that is, if I make the column vector a row vector, I get this form. So this is what I see here is the transpose of transformation from A frame to B frame. Or this shows the transpose of the projections of XA in the B frame. So this one, the column, shows the projections of XB in the A frame, and the row shows the projections of XA in the B frame. So a lot of information, as you see, is hidden in this rotation matrix. And this is the nice thing about mathematics, because just this mathematics speaks itself, and gives you all this hidden information, and this may be very lengthy and not so precise explaining it in English, but when you look at it in the mathematics and when you can decode the mathematical language, you see there is a very nice structure here, and in this structure is embedded a lot of information. And this is going to be meaningful to you because you are engineering final year students when you see how you can implement this information in solving some problems. Okay, let's now summarize what we've seen. We have been seeing that the transformation between a moving frame B and a fixed frame or reference frame A, or A can just be the previous moving frame, and if I talk in more general terms, the transformation of the B frame to A frame, where these frames can be moving frames or fixed frames, is expressed by a matrix which is composed of rotational part and positional part. The position vector is this, and the rotation information is represented by this part. And we have seen that the first column shows the projections of the XP in A frame. Second column shows the projections of YB in the A frame, and finally the third column shows the projections of ZB in A frame. So this is how we in more concise form represent them. Projections of B XP in A frame. In other words, the transformation of BAX from B to A, Y from B to A, and Z from B to A. Always we are showing the original point by subscript and the target by superscript. So that's we are going from B to A in this case. Okay, and we have figured out in the previous slide something very nice, that this is actually the dot product of two vectors X is in the XYZ, the X frames, the A frame coordinates or axis, A frame axis. This is dot product or multiplied with the transpose of the axis of the B frame. And we have seen that this dot product gives this. And we have also figured out that this first column shows the projections of the BXP in the A frame, and the second shows the projections of YB in the A frame, and the third shows the projections of ZB in the A frame. And what was the first row showing? It was showing to us the projections of XA in the B frame. But of course it was showing it in the transpose form because this is a row vector, not a column vector. Okay, now let us try to see how we can implement this. Now what do we see here? In this example, we are seeing a frame where a point P is established in a location which is obtained by the rotation of 45 degrees about the z-axis. We can see that the second frame, or the B frame, rotates with respect to the first frame about the z-axis by an angle of 45 degrees. Let's see how we can handle this. Okay. If I now think that this point is on the y-axis of the B frame, then the xb is going to be also making 45 degrees with xa, like yb is going to be making 45 degrees with ya. Then zb and za are of course coincidental because the rotation is about the z-axis. Okay, now we already know this. The rotation, in this case there is only rotation, there is no translation, and the rotation about the z-axis is given by this matrix. And this matrix, when we put 45 degrees into the theta in this matrix, it gives these numerical values. And if this point yb is 5 units away from the origin, so its components are going to be 0. There is no component in the x direction, there is no component in the z direction, are going to be 0, 5, 0. Just making matrix multiplication is going to give me where it is with respect to the a axis or a coordinate system. This is how we obtained it from the rotation formula we had seen. But now we have learned that this rotation formula or this rotation matrix actually comes from the dot products. Now let us see if we get the same result by looking at the dot products. Now xp dot xa, xp dot xa is cosine 45, yb dot xa, and yb dot xa is cosine 135, zb dot xa, zb dot xa, and this is zb is orthogonal to xa, so this is 90 degrees and cosine 90. Similarly, xp dot ya, 45 degrees, so cosine 45. yb dot ya is another 45 degrees, cosine 45. zb dot ya is cosine 90. zb ya 90 degrees, of course, cosine 90. xp dot ca is another 90 degrees. Why? Because xp is in a plane which is perpendicular to za, cosine 90. yb dot za is also 90 degrees because again za is perpendicular to the plane on which yb is. And finally zb dot za is cosine 0 because z and zb are aligned. Okay, so we see that we get the same result. So now at this stage you understood where these rotation matrices come from. In lecture 1 we have tried to derive this by using simple geometry, but here in this lecture we saw we can get it much more systematically by using vector matrix mathematics. So this mathematics, vector matrix mathematics, makes it much more systematic and convenient to actually derive the same formula. And we found the result. So this is going to be rather practical in solving problems which like the problems we see here. For instance, in this case we are asked to find the transformation matrix between these two frames. Now the geometry, do we need to worry about the geometry much? Actually what we need are just the angles, and if we just figure out the angles, we can put the angle information into the formula we have obtained in this part of the lecture. Then we get the result. Now the angle information is given to us here. Okay. Now let's see how we implement this angle information. Now we know that the rotation matrix from B to A are given in terms of dot products. We have seen it in detail in this part of the lecture, and we just now put in the angles. What is the angle between XP and XA? Now XP and XA, the angle between XP and XA is obviously 90 degrees. YB and XA. YB and YB is this, YB, and XA is this. So this is 90 plus 30, which is 120 degrees. ZB and XA. And ZB is this and XA is this. This is 30 degrees. Now I'm not going to continue with the rest because you have got the idea, but make sure that you check the results for the following entries of the matrix. But you see, this type of representation makes it rather easy for us to solve a complicated looking problems like this. So if you just figure out the angle between the axis of the later frame and the previous frame, then this approach gives you the transformation matrix, or at least the rotational part of the translation matrix, with rather systematically. Now that we found the rotation matrix from B to A, what is the transformation matrix from B to A? For the transformation matrix, we need the displacement information. Now obviously we see there is not much in the, there's nothing in the y direction, therefore it's going to be something in the x direction and the z direction. So okay, so I should actually correct this part. Now I put I thought that this was the y-axis while writing it, but this is the z-axis, so it should be 8.66 in the x direction, 0 in the y direction, and 5 in the z direction. So this is going to be the transformation matrix. But this is a careless mistake. So the 5 and 0 should be exchanged. Okay, this concludes the part 2 of lecture 2.